Today we're going to be talking about equivalent resistance. That's just a way of saying the total resistance that a circuit has. So in the picture here I have two different circuits that you should be familiar with by now. On the left-hand side I have a circuit, and there is just one pathway for the current to take through that circuit. So if you imagine the switch being closed, you can imagine the current following along this one pathway. That makes this a series circuit. On the right we have a very similar circuit with a battery, a switch, two light bulbs. So that's very, very similar, but the pathway that the wires have been arranged in is slightly different. You can see here on the right there is more than one pathway that the current could flow through. As it goes, again, if we close the switch, the current could go this way through the battery and through one bulb, or it could go this way through that second bulb and battery. So that makes this circuit a parallel circuit. So we want to be able to understand how does the arrangement of these circuits influence the total resistance in the circuit. So we've already had some experience with this, but let's review by looking at the online model that we've used before to build these circuits. So if we're trying to figure out what's going on with the current in these two different models, we can think about some ways to look for that. So you'll remember that one way to look at what's happening with the current is to think about the bulb brightness. How bright is each of these bulbs going to be compared to each other? Are they going to be the same or different? Which will be brighter or dimmer if they're going to be different. Another way to think about that with this model, since we can see the electrons, will be to actually just look at how are the electrons moving. Is one on one circuit, is it flowing more quickly or more slowly than the other? That will give us a really good idea of what's happening with the resistors and how much resistance there is, because resistance, remember, is it's like the opposite of conductivity. The opposite of that charge being able to flow is the resistance. So as we close the circuit here, we can look at the resistance in this first series circuit. So you can see the electrons are moving fairly slowly along that whole path that we talked about. Notice that the speed of the electrons everywhere in this path is the same. That's going to come back and be very important for us. So we know the current everywhere in this is the same. The bulbs have the same brightness, and you can see they're not very bright. The lines here aren't very long or thick. So make a guess, a prediction. What do you think is going to happen in the parallel circuit when I close that circuit? How's the speed of the electrons going to compare? How's the brightness of the bulbs going to compare? All right, let's check and see if you were right. Did you think that the bulbs would be brighter? That tells us this has more overall current. Also, you can see the current itself, as shown by the electrons, is much quicker than it is over in this series circuit. Another important thing to think about, and again that will come back later on in another lesson, is this idea that the current is not the same everywhere in this parallel circuit. You can see that the electrons are moving very quickly through this part of the circuit, and then less quickly when the circuit branches into these parallel branches here. It's going more slowly through each of these branches than it is in this part of the circuit where it's connected to the battery. So keep that in mind again for later on. So we know, even though each of these has two resistors, and they're identical resistors, they're 10 ohm light bulbs in each case, they're acting differently in these circuits. So we want to try and think about why that would be. So to think about this, let's go back to an example that we've used earlier in the class of straws. So we thought about having a straw be a model of a resistor. So we know that a thick straw represents a low resistance resistor. It's pretty easy to blow or breathe through a thick straw. The thicker it is, the easier it is to blow through. Now we're going to use all small straws as a way to try and think about the resistance and what's happening with the resistance. So in a series circuit, it's kind of like we've taken one resistor and now we've stuck another resistor in series with that. So we've made instead of having one short resistor, we now have one much longer resistor when we've added a resistor in series. And hopefully, again, you can get an idea that it would be much more challenging to breathe through one long straw than it would to breathe through one short straw. Or imagine if I really took that to the extreme and I made a really, really long straw, that would have much more resistance than just one short segment. That's what's happening in series resistors. When we add resistors in series, it's like stacking straws, making the length longer and longer and longer. Contrast that with parallel circuits. When we have a parallel circuit, we're making an additional pathway for the current to flow through. So instead of being like stacking straws together end to end, it's like putting straws side by side. Now imagine taking two straws and breathing through them side by side. Is that easier or more difficult than when you have just one straw? Hopefully you can see that would be more much easier to breathe through, and you could take that out again to the extreme. What if I have 4 or 5 straws all side by side and I'm trying to breathe through all of those all at once? I have way more pathways for the air to flow through, so it's much easier to breathe through this kind of straw in parallel than it would be to breathe through a straw in series. Same exact idea is happening within these circuits. So when we have resistors in series, that makes it harder for the current to flow, so it's more overall resistance or more equivalent resistance or total resistance. When we have resistors in parallel, like here, we give more pathways for the current to flow through, so we actually reduce the overall resistance, like having multiple straws to blow through. So let's look at how we calculate the specific equivalent resistance. So anytime we have a set of resistors and they are in series, we can calculate the total resistance by simply adding the resistance of each resistor. So here's the little formula. The total resistance is equal to the resistance of resistor 1 plus the resistance of resistor 2 plus ... That can go on for as many resistors as you have in the series. So if I have an example where I have this very simple circuit, I've got a 5 ohm resistor here in series with a 10 ohm resistor. Go ahead and try and figure out what would be the equivalent resistance of this circuit. Hopefully you saw that this would just be 5 ohms plus 10 ohms, so the equivalent resistance or the total resistance of this circuit would be 15 ohms, which is exactly what we predicted. This is like taking two straws and sticking them in series, so we have a higher overall resistance than either of the straws by themselves. That's equivalent resistance for a series circuit. How about for a parallel circuit? Well, for a parallel circuit, we should have a smaller equivalent resistance, right? The overall resistance should be less than any of the parts. So we find this by taking what's called the reciprocal. You might remember that in math, reciprocal just means to take a fraction and flip it upside down. So if I have the number 5, we could write that as a fraction as 5 divided by 1, or 5 over 1. So if I want the reciprocal of that, I would flip the 1 on top and the 5 to the bottom, so that would become 1/5. Many of you have scientific calculators, and in your calculator there's a little reciprocal button. It looks like this. So lots of times it will say x to the -1. So x to the -1 power, or any number to the -1 power, is the reciprocal. That's what it means to take something to the -1 power. So there's 2 different ways we can write this. We can write it as 1 divided by, and then the reciprocal of each resistor added together, or we can write it as, in this format, the resistor to the -1. That means the reciprocal of that resistance plus the reciprocal of that resistance, and then we need to take the reciprocal in the end. So again, this might make more sense with an example. So here we go. You can see the same kind of simple circuit we had before with 2 different resistors, a 5 ohm and a 10 ohm resistor. How would we take the overall or equivalent resistance for this circuit? Well, hopefully you came to the conclusion that we would need to take the reciprocal of each one of these resistors, the 5 ohm and the 10 ohm resistor, and then we would take the reciprocal of whatever we add up there. So the reciprocal of 5 is 1/5, plus the reciprocal of 10 would be 1/10. So 1/5 plus 1/10 would be 3/10. And then we have to take the reciprocal of that, so that would be 10 divided by 3, or 10 over 3, which we could do the math, and that would come out to 3.333. Or if you're thinking about this, how you're going to put it in your calculator, you're probably going to put it in this form. So you would have 5 to the -1 plus 10 to the -1, and then you take the reciprocal of that. After you do that, you would come up with the exact same answer of 3.33 ohms. Again, check your understanding with our straw model. Since this is in parallel, we should actually get less resistance than either of these by themselves, right? So, and that's exactly what happened. 3.3 ohms is less than either 5 or 10 ohms. All right, so good luck with your practice problems. Let me know if you have any questions.